Hey class, Adam Ward here. I want to work with you through an anaerobic digester design problem. And so on the slide you're seeing quite a lot of given information and the 6 items A through F that we're going to try to calculate in this problem. What I want to point out here in red is that this is a microbially mediated problem. We're designing a reactor to make sure those microbes, the methanogens in this case, have time to complete the processing that we'd like them to complete. And this very first part of the design problem is exactly parallel to the activated sludge process. One other note before we really dive into the calculations here, you can see the minimum operating temperature spec'd out is 16 degrees Celsius. And this is really important because that minimum temperature is going to give us the slowest rates. And so we always want to think through what is going to be the lowest operating temperature that we'll have in a given, in a typical year, so we can make sure that our design is going to be adequate even under those worst case conditions. Okay, so what we're going to do tonight then is move forward through parts A through F, and we'll start with the minimum and design solids residence time. So this equation should look familiar to you from activated sludge design. So 1 over our minimum residence time equal to, and you can see the right hand side is those combinations of substrate loading rates, half saturation constants, growth rates, decay rates or death rates, and yield, the capital Y. So just quickly taking stock here, that minimum retention time is what we're looking for. Yield and substrate load we are given. And then there are 3 items where we're going to need those values at 16 degrees Celsius. And we were given the equivalent values at 35 degrees C and the Arrhenius equation information. So we'll have to make some conversions. So the first conversion up will be our growth rate. And using the Arrhenius equation, we remember that we just need to convert from 35 degrees to 16 degrees. So we can go ahead and plug in our given value, 6.67 pounds of BOD per pound of volatile suspended solids per day, multiplied by that Arrhenius constant theta, 1.035, raised to the 16 minus 35 degrees C power. And out of that, we get a value of 3.47. Just one thing to point out on here, we know that we're converting to a colder temperature, so that gut check that we want to make is that we're getting a slower rate or a smaller value here. 6.67 is what went in, 3.47 came out, passes the gut check. If we had found a larger number, it's almost certain that your problem would have been up in that exponent. You might have reversed the 35 and the 16, for example. Okay. We'll do that same conversion with our half saturation constant, converting from 1.8 grams per cubic meter at 35 degrees centigrade to 0.24 at 16 degrees. You can see that's an incredibly sensitive term, and we could have known that going in because that theta value is particularly high compared to what we're accustomed to working with. And I'll go ahead and just make that conversion from grams per cubic meter to 1.5 times 10 to the minus 5th pounds per cubic foot. And that's just to get the dimensions on that term homogeneous with the rest of what we're doing for this problem. Finally, for KD, that death rate or endogenous decay rate, we'll go ahead and go from 0.03 per day at 35 degrees C to 0.016 at 16 degrees C. So with those values, this becomes an algebra problem. Go ahead and plug those in the numerator, the yield, our growth rate, and our substrate loading rate, 950 pounds of BOD per cubic foot, the concentration of substrate coming in, I should say. In the denominator, our half saturation constant, and again, that concentration of substrate minus the endogenous decay rate. And if we do our algebra correctly, or if I did mine correctly, I should say, I ended up with a value of about 8.14 days. And so that is the minimum retention time, right? And we'll remember what that means is if the residence time in our system is 8.14 days, that's sort of that perfect threshold where the rate at which methanogens are being washed out is exactly equal to the rate at which they're reproducing. For design purposes, we're going to use a safety factor to make sure that we're well above that. And we were given a safety factor of 2.5. So it's as easy as multiplying that 8.14 by 2.5, and you get a value of about 20.4 days. All right, so that is parallel to what we've done before for the aeration basin. That should look pretty comfortable for everyone. Volume of the digester, we can use our residence time equation here. So residence time being equal to the volume of our digester divided by the flow rate of sludge entering. 20.4 days equal to the volume divided by the volumetric flow rate of sludge, 1,036 cubic feet per day. And I get a volume of about 21,100 cubic feet for the digester. As we typically do, we're going to just do a check that we're within typical ranges here. And in this case, it's the loading rate per volume. So the mass rate that we're loading our sludge divided by the volume of our digester. Mass rate was, excuse me, the mass rate was 3,266 pounds per day. Volume of 21,100 cubic feet in the denominator there. And I get a value of about 0.155. And that is within the typical range, so that makes me happy. If we're getting above that, particularly as we approach a value of about 0.2, that's where we again start to worry about washout. And so these are basically checks to make sure that we are providing sufficient time for the biological process, the methanogens, to take all of that organic carbon and basically reduce it down into methane. So we want to make sure we're keeping those microbes sort of happy, providing them a sufficient habitat and time scale to achieve the function that we want from them. Okay, so with that design in place, now we can look at the performance. So estimate volatile suspended solids removal as a percentage as well as a mass per day. And so as a percentage, we can sort of boil this down into the empirical estimate provided here, which you would have read about in your textbook. That percentage on the left-hand side is equal to 13.7 times the natural log of that design residence time plus 18.9. So if we go ahead and plug in 20.4 days, my calculation yields about 60.2% removal of volatile suspended solids. Well, that's a percentage. To get the mass per day, we can take the mass of combined sludge that's being input, so 3,266 pounds per day of combined sludge, and combined meaning it's coming from both the primary and secondary clarifiers. We were given that each pound of that combined sludge contained about 0.7 pounds of volatile suspended solids. And we know that for every 1 pound of volatile suspended solids, about 0.602 or 60.2% will be removed. So we can work through that calculation and I get about 1,376 pounds of VSS per day. In other words, that amount of volatile suspended solids is turning into gases in the digester. So we're getting a pretty substantial removal of the solids within that sludge. We're converting more than half of those into gas, and much of that gas will be in the form of methane. That makes us happy because that's a resource. Well, part E is going to start dealing with that resource, the gas generated. How much do we produce? And so we were given a range of gas production rates, and so what we'll do on this slide and for the rest of the problem is explore both of those. So at the low end, we estimated 0.8 cubic meters of gas produced per kilogram of volatile suspended solids. You can see that I'm multiplying that by the amount of volatile suspended solids that we degraded, 1,376 pounds per day, and the conversion factor from kilograms to pounds. And that suggests we're going to produce 500 cubic meters of gas per day. If we pick the other end of that range, 1.1 cubic meters, you'd end up 1.1 cubic meters per kilogram that is digested. you'll end up with 688 cubic meters of gas per day. And so I'm going to continue pushing forward, and I'll use black for the low end of that range and blue for the upper end of that range, just to keep things straight. Finally, we're asked to assess what might be the electrical potential if we took that gas and we captured the methane and turned that into electricity. So that would be essentially piping it into a natural gas electrical production plant or power plant. Well, we were told gas from the digester is typically 65% methane. And so I can take those two values above, multiply them by 0.65, and I find that anywhere from 325 to 447 cubic meters of methane per day could be generated. We were also given that methane contains about 39 megajoules per cubic meter. And so that suggests that on a daily basis, we're anywhere from about 12,700 to 17,400 megajoules that we can yield in terms of the total energy within the gases. And just to really be clear here, this is total energy in the methane gas. That's not the energy that we can effectively use as electricity. That's the total amount of energy that's caught up in those bonds. Converting units from megajoules into kilowatt hours, just to get this into units that you're perhaps more comfortable working with, thinking about electricity, anywhere from about 3,500 to about 4,800 kilowatt hours per day. Again, that's in the gas. If you actually use this for electrical generation, we have about a 25% efficiency, meaning we capture about 25% of that energy as usable electricity. And so multiply the two numbers above by 0.25, and you should end up with about 880 to 1,211 kilowatt hours per day. So by digesting all of that sludge, we're able to generate somewhere between 880 and about 1,200 kilowatt hours every day. Now, that doesn't mean a lot to me. I don't work with electrical values a lot. So just as something to give you some context here, the typical home in the US uses about 29 kilowatt hours per day of electricity. So that digester provides all of the electrical energy it would take to power somewhere between 30 and 41 homes. That is a pretty substantial amount of electricity. We're not going to probably meet society's electrical needs by digesting our waste sludge, but that's not an inconsequential amount of electricity. And rather than vent that CH4 into the atmosphere, turning it into electrical energy is a great opportunity. Now, the other thing that I'll point out to you here is as we went through this conversion, where I'm drawing this bright pink arrow right now, we lost 75% of that energy. We didn't recover it as electricity. So just as a reminder, that 75% is not all, but largely going to heat. And so using that methane gas to produce heat, for example, to heat a building, for cooking supply, for controlling the temperature of the digester itself, is another really good use of that methane. So rather than going through those steps to convert to electricity and losing it, actually piping that back into our natural gas system and using it for direct burn might be a better way to make use of that energy. All right, folks, so I hope that this helped you out. The goals for this exercise were to help you see the parallels between the aeration basin design and the sludge digester design, both microbially mediated processes where we've got to think about things like yields and saturation constants and growth and death rates, and secondly, to provide some context of just how much energy can be recovered from these systems by digesting the sludge that was a waste product from our treatment processes. All right, hopefully this helps, and I will see you all back in class. Thanks, everyone.